To create a 3 by 3 magic square, do we always have to use only the numbers from 1 to 9? No. Then, what is the actual rule behind creating a magic square? To understand that, first let's learn about arithmetic progression. Look at these number sequences. Here, every step increases by 10. Here, increases by 3. Here, the numbers are decreasing. Each step reduces by 5. All these sequences follow one common idea. The actual numbers are not important. The important thing is the difference between consecutive numbers must remain the same. That difference can be positive, negative, small, or large. But if it stays constant, that sequence is called an arithmetic progression. Now comes an interesting question. What is the connection between arithmetic progression and magic squares? Let's look at the famous Lo Shu Magic Square. The numbers used are 1 to 9. This is also an arithmetic progression because the common difference is 1. From this, we understand an important idea. Arithmetic progression can be a good starting point, but the real beauty of a magic square is not just in the numbers. It is in how those numbers are arranged. Using the same arrangement idea, we can create magic squares with different sets of numbers too. Now, when we carefully observe Ramanujan's 4 by 4 magic square, it gives us a different way to look at magic squares. If arrangement is the important part, should we always think about the grid and the numbers together? What if we study the grid separately and the numbers separately? This leads to a deeper question. Is the pattern only inside the grid, or do the numbers themselves contain some hidden mathematical structure? Questions like these help us see magic squares not just as simple number puzzles but as a deeper area of mathematical exploration. Now, an important question comes up. Do numbers always need to follow a fixed pattern to create a magic square? For example, look at these numbers. This is not an arithmetic progression. There is no common difference between them. At first glance, it may look impossible to create a magic square using numbers with no obvious pattern. But Ramanujan's 4 by 4 magic square shows us an interesting mathematical idea. Even when numbers do not follow a simple sequence, a carefully designed mathematical arrangement can create balance. To understand this idea, let's imagine a farmer. A farmer divides his land into 16 sections. Before the rainy season begins, he first plans the complete layout. Where should the boundaries go? Where should the water channels be placed? How should each section be organized? At this stage, the land is empty. No seeds have been planted yet. Only after planning the structure does he decide which seed should go in which place. The season may change, the crops may change, but the basic structure of the land remains. In a similar way, a magic square can be built using a mathematical structure first. Then values can be placed into that structure. For this kind of construction, mathematicians can use variables like a, b, c, and d. A change in one place can be balanced by another change somewhere else. This balance keeps the magic square consistent. Even if some values change, the mathematical relationship can remain the same. Now, inside this structure, if we place 22, 12, 18, 87 in the first row, they represent 22 December 1887, the birth date of Srinivasa Ramanujan. This creates the well-known Ramanujan birthday magic square. In this square, all rows, all columns and both main diagonals give the same magic sum. But magic squares contain more interesting mathematical patterns. Let's take the Lo Shu Magic Square. The first row, the last row. Now, let's pair these numbers. 8 and 4 become 84. If we reverse it, 48. 1 and 9 become 19. Reverse it, 91. 6 and 2 become 62. reverse it 26. Now let's add one side and the other side. Both sides give the same sum, but the interesting part does not stop there. If we square these numbers and add them, we get another surprising equality. At first, this may look like a coincidence, but behind this equality, there is a mathematical relationship. Finding these hidden patterns helps us understand magic squares at a deeper level. The pattern based thinking behind magic squares created many new questions for mathematicians. One interesting question was, can the ideas of magic squares be used to create even larger magic squares? One area that developed from this exploration is combined magic squares. The special idea behind them is a large magic square can contain smaller magic squares inside it. When we look at the complete square, it works as a magic square. At the same time, some smaller sections inside it can also follow magic square properties. In other words, the same mathematical idea can continue at different levels while maintaining balance. But an even more challenging area is prime magic squares. We know prime numbers like 2, 3, 5, 7, 11, 13. But prime numbers do not follow a simple repeating pattern. They are not like arithmetic progressions, where every step has the same difference. Some prime numbers are very close, like 17 and 19, but sometimes there can be a larger gap before the next prime number appears. Because of this, creating a magical square using only prime numbers is a difficult mathematical challenge. The arrangement must still satisfy the magic square conditions. Every row, every column, and both main diagonals must produce the same magic sum. Many mathematicians continue to explore different types of magic squares and their constructions. In modern research, Professor Inder J. Taneja has contributed to the study of magic squares through different construction methods. His research explores ideas such as creating larger magic squares by using smaller blocks and structured arrangements. Topics like block structured magic square, bordered magic squares, prime magic squares are examples of different approaches studied in this field. But all these studies are not just about arranging numbers. They represent a bigger mathematical idea. Taking a concept, understanding its structure, and using the same idea to create something more complex. Let's understand this with a simple example. Imagine you have Lego blocks. If you throw them randomly, you cannot create a perfect car or house or a robot. First, you need a plan. Which block goes where? Which block connects with another? A pattern and a structure are needed. Magic squares work in the same way. Numbers are important, but more important is the rule that organize those numbers. This same idea appears in computer science too. When a computer solves a big problem, it does not randomly try everything at once. It follows a sequence of steps. Check this first, move to the next step. Is this condition correct? If not, try another path. These step by step instructions are called algorithms. The same type of thinking is used in solving Sudoku puzzles, chess programs, AI, cryptography, and data security. Patterns, rules, balance, structure. These ideas connect mathematics with technology. Computers did not copy magic squares to create modern technology, but the mathematical thinking behind magic squares, such as pattern recognition, logical construction, and balanced design, continues to influence many areas of modern technology. The study of magic squares is not only about magic squares. The bigger idea is how can we transform a complicated problem into a clear and organized structure. Pattern thinking, logical construction, balanced design. These mathematical ideas continue to exist in today's world. Thousands of years ago, humans started searching for patterns in numbers. That search is still continuing today. At first glance, some numbers may look completely random, But with the right mathematical thinking, we can discover hidden order inside them. Sometimes, beautiful mathematical patterns are hidden inside numbers that appear confusing. The curiosity to find those patterns has continued to inspire generations of mathematicians. That is why a magic square is not just a number puzzle, it is an endless mathematical journey.